Hey everyone, it's Elijah, the chemistry tutor from Stanton 101. Today we'll be covering our final lesson of the Thermodynamics/Thermochemistry unit. In this video specifically, we will be covering enthalpy, entropy, Gibbs free energy, and Hess Law practice problems. So first let's start with enthalpy. Enthalpy is basically the change in heat content for a reaction. So to get the enthalpy of a reaction, you need to do the sum of the molar coefficients, or these, times the standard enthalpies of formation for the different substances. And first you need to do the product side, and then you subtract it by the same thing except it's the reactant side. So let's go over this problem, which seems to be the combustion of propane. And to do this, first we need to do the products minus the reactants. So the standard enthalpy of formation for carbon dioxide is minus 393.5 kilojoules over moles. So that's the unit that we'll be using for this, but I didn't feel like writing it out a bunch of times. So then you multiply that by the coefficient for it, which is 3, and then you add the same thing except water, and it's liquid water. You need to make sure you're using the standard enthalpy of formation for the right state of matter. So then you subtract that by the same thing, and propane is minus 103.85 kilojoules over moles, and then oxygen is 0. So then you get your sides, you subtract them. In this case it would be subtracting a negative, so it would technically be adding, and then you get this as your answer. It's negative 2219.9 kilojoules over moles is the enthalpy of this reaction. I did these problems out beforehand because they're a bit easier and I just wanted to save a little bit of time. So next, after enthalpy, we will be going over entropy. Entropy is pretty much the measure of randomness or disorderliness, I don't know if that's a word, of a system. So entropy will grow when it is greater than 0, and this growth can be caused by a growth in volume, a growth in temperature, more complex molecules being formed, an overall growth in molar mass, certain phase changes, such as going from solid to liquid, liquid to gas, solid to gas, and then if the amount of moles of gases that are produced is greater than the moles of gases that are consumed in a reaction, then the entropy will likely have gone up. Now let's do an entropy problem. Now this is very, very similar to the enthalpy problem. It is exactly the same actually. You have a bunch of standard molar entropy values that you can find online, or if you're given a chart, like the values I gave before for enthalpy, those aren't widely known. You'll be provided those, or you'll be allowed to look them up. So it's the products minus the reactants as it was before. So the standard molar entropy for carbon dioxide is 213.6 and the coefficient is 2, so you multiply it by 2. Then you subtract it by 2 times 197.9, which is carbon dioxide, and then add 1 times 205.0, which is oxygen for that. Oh, I think I said carbon dioxide here. That's carbon monoxide. My bad. Then you get these and subtract them, and your entropy change will be minus 173.6 joules over moles times Kelvin, which this is your unit here. It's not kilojoules over moles like it was before. It's joules over moles times Kelvin, which will be important to remember. Now this makes a lot of sense because here you can see that there are 3, or it acts like there's a 1 here, but if your coefficient's 1, you don't really need to put it. So there are 3 moles of gas here, and then it goes down to 2 moles of gas. So if you remember right, the moles of gas produced are smaller than the moles of gas consumed. Therefore, it's the change in entropy is negative instead of positive. And I just put this in as well to show this. This one has 1 mole of gas, and then it goes to 0. So this problem would also likely be a decrease in entropy. And this is just for those who don't get a lot of math problems on their tests and who have a lot of theory. This is a good theory problem because it shows a very common sign of entropy going down, which is the moles of gas consumed being greater than the moles of gas produced. So now we're going on to Gibbs free energy, and this certain parameter is a bit different than the last two that we've done. So when the Gibbs free energy of a reaction is less than 0, that means it will be spontaneous in the forward direction. And then if it is greater than 0, it will be spontaneous in the opposite direction. So say you have A plus B is C. If the Gibbs free energy of this problem was negative, that means it is spontaneous going in this direction, so it's already written as a spontaneous reaction. But if it was positive and not negative, then it would only be spontaneous going this direction, but would not be spontaneous going in the direction it was written. Now the formula for Gibbs free energy is a bit different. It is the change in Gibbs equals the change in enthalpy minus temperature times the change in entropy. So let's look at this problem. It's 2 moles of benzene combusting to be 12 moles of carbon dioxide and 6 moles of water in liquid form. Now what I want you to do as you're viewing it, I want you to calculate the enthalpy, and I want you to calculate the entropy, and I gave all the values for you. Here, these all correspond with each other going up. So just do this problem, find the delta H and the delta S, and then we will find the Gibbs free energy. So now you have hopefully done the problems, and when I did the problems, I got the enthalpy of the reaction as negative 6,535 kilojoules over moles, and then for the change in entropy, I got negative 439.2 joules over Kelvin times moles. Of course, let me know if you got different values, just say in the comments below. Now, when you plugged this into the equation, you got your enthalpy value, then you got your minus temperature value, which is standard, 298 Kelvin or 25 degrees Celsius, as they may give it to you a lot, but you need to write this in Kelvin, that's important. So then you multiply that by the kilojoules, and for this it's 0.4 kilojoules rather than 400 joules because you have to convert it into kilojoules form to match the enthalpy. So that's kilojoules over Kelvin times moles. Kelvin cancels out. The answer is in kilojoules over moles, and it's negative 6,404.1 kilojoules over moles. And since it is less than 0, that means that this is a spontaneous reaction. Okay, so let's move on to our final part of the video, which is Hess's Law problems. Now for this problem, it's saying to find the change in heat for 4 moles of ammonia gas plus 5 moles of oxygen, which turns into 4 moles of, I think it's nitric gas, plus 6 moles of water gas. And then it gives you a couple of other things, which is different conditions if nitrogen plus oxygen equals 2 moles of nitric oxide with the enthalpy value of negative 180.5 kilojoules, and then a few more like that. Now the key for these problems is knowing how to balance these out. So we need to see what's produced here, what's produced here, what's consumed here, and what's consumed here. So here we can see that oxygen is on the reactant side, as it is in the problem that they want you to solve, and that nitric oxide is on the product side, as it is in the problem they give you. So then to make it match up, since there are no other nitric oxides in this problem, you're going to need to multiply. Here, I'll just do it up here. You're going to need to multiply this by 2, which will make 2 nitrogen plus 2 oxygen, and then we'll go into 4 nitric oxides, and then eventually we'll have to multiply this by 2 as well. Now let's do the same thing for the second problem that they give us. Now this one is a bit trickier because we're going to need to reverse it, since we need the ammonia gas to be on the reactant side. And this also means changing the symbol here to positive. I don't know why I crossed it out like that. And then we're going to need to multiply this one by 2 as well, because we need to get a value for the ammonia gas that is equal to as it is in the problem shown. So that'll be plus 4 NH3, and then on the other side plus 6 H2 plus 2 N2. And now for the final problem, we'll be doing the same thing again, except this time multiplying it by 3, because we need to get 6 waters, and we only have 2 here. So multiply that by 3 to get 6, and that makes 6 H2 on this side, and then 3 O2s. And then on this side, 6 H2O. Now at this stage of this problem, I know it looks really jacked up because I wrote it, but we will need to do some multiplication up here, and we're going to need to do some canceling over here. So first let's do the canceling just to keep it simple. These are obviously spectators because they're on both sides, and then the hydrogens are also spectators because they're on both sides. Then when you add these up, it becomes 5O2 plus 4 NH3, and that becomes 4NO plus 6 H2O, like it originally was up here. Now we need to do some multiplication. Negative 180.5 times 2 will be negative 361. Remember, this is now positive, and 91.8 times 2 will be 183.6. And finally, negative 483.6 times 3 will make negative 1,450.8. Then this is all in kilojoules, all of these. So the final answer will be a combination of these in kilojoules, and that, let me do some quick calculator work, will be negative 1,628.2 kilojoules for the change of heat for this reaction. So in the end, it balanced out perfectly and gave us a good number. Now thank you so much for watching. I'm sorry that this video is coming out a bit later than it should have, but hopefully it helps for some last minute review. I know it certainly helped me to go over a few of these problems, and we will be moving on to our next unit very soon. Thank you again for watching. Hopefully it helped, and goodbye.